This video is an introduction to a new project I'm starting, and it's something that I'm hoping a lot of you might find interesting, and the outcome may even be of some use to you. If you've been watching my channel, then you'll know that I restore and repair vintage equipment, old computers, teletypes, teleprinters, that sort of thing. And one thing that's a constant whenever I'm doing this is the need to be able to fault find on fairly complex digital boards. So the one I'm working on at the moment is this one. This is the main processor board out of a REN computer, and normally I have 5 or 6 projects on the go. They're all fairly similar in the approach I take, and often I don't have schematics or any technical information, so it's really figuring out how the circuits work, finding my way through them, finding the faulty devices, replacing them, doing more testing, writing firmware, this sort of thing. And one of the things that I've been meaning to get hold of for many years now, and I haven't done because of the cost, is a device to allow me to test ICs while they're still in circuit. On an average project, I'll change anything from between 1 and maybe 100 faulty devices, and tracking them down can be a bit tricky simply because without a schematic, what I'm ending up doing a lot of the time is doing a pin in, pin out check with a scope or logic analyzer to see if the device is doing what I expect it to. And quite often that can be tricky because if the device is currently inactive, then it's hard to tell whether it's faulty or not. Now what you can do when you get a device that you suspect is faulty is remove it from the board, use a device like this to test it, and then if it's faulty you can replace it. But of course removing devices from multi-layer boards is quite difficult, and especially old boards where you're in danger of lifting the tracks. There are devices around that you can purchase that are called logic comparators, and what they essentially do is you give them a known good device. So you take a device that you know works and you'll plug it into your tester, and then it will compare the performance of that device against one in the PCB. So you'll hook a test probe to the device in the PCB, put an equivalent working device into the tester, and then you just let it run to see if they are both doing the same thing. And if they're not both doing the same thing, and you know that the one in the tester is working, then you know that the one in the PCB is faulty. That's the principle. It doesn't always work because sometimes devices on PCBs are affected by external influences, but it still gives you a very good indication that something is wrong in that part of the circuit. The reason I have never bought one of these is due to the cost and also the limitations that they have. I looked on eBay this morning and the cheapest one I could find, in fact there was only one, was upwards of £600. It was in the US, so by the time I'd paid import duty and shipping it would have been up around £1,000, and it would still only test devices that had up to 16 pins. The way they work is actually extremely simple. It just uses a simple logic comparator for each pin. The only complication is deciding which pins are power pins, and most of the devices available get around that by having module boards that you would configure with your known good device, and on the board you set or you link the power to certain pins so that the power is always going into the test device on the same pins. And what I've decided to do, rather than holding out any longer for one of these devices, is I'm going to develop and build my own. And of course once I've done that, I will make the boards for it available on my website, so anyone that wants to build their own will be able to do so. But I thought it would be interesting to go through the development process right from the start, and going through the kind of thinking process and what I want the device to do, right through to the schematic design, and then pre-production, prototyping, testing, and then, as I say, if you want one you can simply get a set of the boards. The approach I'm taking is to use the simple NOR comparison method, and all that really entails is you have 2 inputs for each pin of the devices you intend to test. There is one input comes from the device on the board, that's the unit under test, and the other input comes from your known good device. Now I've got a mock-up here of a single pin for the tester. All the pins would be identical, apart from the power pins of course. So the actual part of the tester are these three devices. This is just one pin, but these devices would cater for up to 4 pins, and then I just duplicate this depending on how many pins I want the tester to be able to handle. And the way this works is it's not just a static test, it's not just seeing if both are high or both are low in a static mode. This is dynamic. So at the moment, as you can see on the scope, I'm feeding a 1 kilohertz signal into the tester. I have my device, my comparative device, that's the known good device, plugged in here, and again you would normally plug that into your test unit. It's whatever device is the same as the one you're testing on the board, and then this breadboard over here is simulating my unit under test, and I've got the same device as I have over here for comparison. We're feeding a 1 kilohertz square wave into it, but it could be pretty much any signal. And this is the point, the signal's irrelevant, as is the nature of the device. All we're doing is a pin for pin comparison, so this could be a logic device, a memory device, even DRAM, SRAM, a microprocessor, a shift register, a flip-flop. The beauty of this method is that if one device is supposed to do something and you have an equivalent device and they're both fed with the same inputs, then the output should be the same. And that's what we're doing with this circuit, is the LED on the right here will illuminate if the two inputs vary, and I'll simulate that by removing the device on the board to simulate it being faulty, and then I'll put back a different device that doesn't match this one, and in theory if this circuit's working then the LED should come on. Also note the two signals on the scope. This scope is just monitoring the two inputs to the comparator. The amplitude is irrelevant, it's really looking at the logic states, but you could tailor this for amplitude. I've got it set up here just for the midpoint of TTL. So I'll remove the device from my unit under test. I don't advise you normally do this with the power on, but I'll do it here. I don't think it will cause any damage, and you can see that immediately the LED has come on. And what I'll do now is I'll put back a different device. This will simulate the device being faulty. I have chosen a device that won't be damaged by this, but because it's not the correct device, it will behave in a way that doesn't match the comparison unit that we provided. So I'll plug this in, and you can see that although there is a signal on the scope from both channels, it's giving an error because it's an incorrect output. I'll now put the proper device back in, and the LED goes out because we're now getting the correct signals. This will work on every single pin on the device, and as I said, the idea here is it doesn't matter if it's a logic device, and it's also dynamic. If I change the frequency of the meter, and I'll go here up to 1 megahertz, you can see that we are still getting a no error indicator. Again, I'll simulate a faulty device by removing it, and you can see that now we've got an error light coming on because the device isn't matching what is expected. This is not the same as a tester like this. A tester like this applies test signals to the device. We're not doing that. What we're doing is we're simply comparing the performance of the device against the known good one. Put the device back in, the error light goes out. So what the tester will comprise of is a number of these circuits, and it will be arranged in a logical fashion so that when you put a device in, you'll have an LED that's in the right place relative to each pin. And so when you have your test device plugged into the tester, then if there is a discrepancy between its performance and the one on the board, the correct LED will light up and tell you which particular pin is not matching what's expected. But as you can see, because this is dynamic, then it will work on active circuits. And as I said, it doesn't need to be a static or fixed logic. It can be shift registers, memory, microprocessors, anything like that. And my intention is to go up to 40 pins. So rather than the 16 pins that seems to be the limit for most of these testers, I'll go up to the full 40 pin, and then you'll be able to plug in either a 16 pin clip to clip onto ICs, or a 40 pin depending on what you're testing. That's the plan. Just to briefly explain the circuit, it's not just a simple NOR gate or OR gate. What we have here is initially a delay of a few picoseconds, just to make sure that if there is a discrepancy between the timing of the two devices, i.e. if they're different manufacturers or ages. I've mentioned before that as ICs age, they tend to slow down, and we don't want that being indicated too early as a fault. At some point, if it gets too slow, then it should indicate as a fault. So to that end, I've selected a timing delay of so it's actually about half a nanosecond, and that is what I deem to be the limit for my tester, but you'd be able to tailor that for whatever you want. There's then a pulse stretcher, so even if we only get a very brief discrepancy in the signal, again this could be down to timing, then the pulse is stretched and the LED will come on. And just to show you the pulse stretching, if I turn the frequency down that I'm feeding into this to 1 Hertz and then remove the device, you can see that the LED is flashing, and this is just because it's on for the duration of the pulse stretcher. Then it goes off, and then the next time around it comes back on again. So if it's flashing, then it's a fault. I'll put the device back in, and again it stopped flashing because it's getting the correct signals. So you can either use it in a static mode or you can use it in dynamic mode, and the maximum frequency will depend on the layout of the tester and the length of the test cable. So I estimate at the moment it should work up to about 5 megahertz, but I'll test that with the final unit. So any comments are welcome. I'll produce update videos as I progress through this. I'm hoping it won't take too long. What I want out of this is a test unit I can use to properly test ICs while they're still in boards without having to remove them first, and I think that will greatly speed up the testing process. It will also allow me to test things that I couldn't test even if I remove them. So for example, certain memory types, DRAMs, unless you have a specific tester for them, the only way you can test them is by substituting them, and if it turns out they're not faulty, then you've wasted a lot of time and potentially damaged the board by trying to get them out.